And also, I has an IHP for Carmen Fellowship, so I'm here on sabbatical for the whole year. So it's really great to be here, and so come and talk to me if you're interested about talking about statistics. Okay, so this is joint work with Marius and Ben. Here we go. Okay, so today I'm going to talk about a full Bayesian method for inferring the tensor to scalar ratio R from lens CMB polarization observations. So I wasn't sure is the ratio of statisticians to cosmologists. So I'm just going to give sort of an abbreviated sentence or two about what R is. So effectively, if R is greater than 0, this would imply a detection of primordial gravitational waves in the CMB. And it's been called the smoking gun of inflation. So it's a major target of the next generation stage 4 CMB experiments. So planning is currently underway. Okay, so at least from my perspective, this estimating R from CMB field polarization observations is a difficult task, and it's something that I've been thinking about for a long time. It's actually really a privilege as a statistician to be able to work with a process and data like this. It's extremely pristine. I'm not even sure it'll be easy for me to go back to analyzing real data from the environment, et cetera. It's, this stuff is so beautiful that it's going to be hard to walk away from it. So, so I'd characterize the difficulty in getting constraints for this tensor to scalar ratio as due to foreground contaminants that confound this gravitational wave signature. So these contaminants, mainly lensing and then foreground emission. So I'm going to talk about the lensing contaminant today and sort of the problem of estimating and lensing and then delensing it as well. All right, so outline and with a few of the themes that I'm going to try and get across in these sections. So first I'm going to talk about the posterior on this single parameter R given the observed CMB polarization. And I'm going to try and talk about, in a general sense, the connection between posterior versus prior marginalization and its association with inference tractability. And then I'll talk about a new mixed flow reparameterization technique that we've recently come up with that I think was the key that sort of opened up samples. And here I'm going to try and emphasize the connection between model parameterization at Gibbs chain mixing time. And then present a tractable, fully Bayesian solution to delensing and R inference jointly. And I'm not sure if I'll have time, but maybe talk more about this lens flow algorithm towards the end. Okay, so first the posterior on R given the observed CMB polarization. Okay, so this is the basic data setup that I'm going to be working with for the whole talk. So it's going to be flat sky simulations, and I'm ignoring foreground emissions, which is a really important problem that I actually plan to work on while I'm here as well. But I think the lensing, delensing problem is hard enough, so that's what I'm going to work on or present today. Okay, so this is the format for the data. D is the data. Okay, so this F here is just sort of a coordinate agnostic way to write the unlensed polarization field. So this is a Gaussian random field, mean 0, with covariance operator given by this CFF that depends on this tensor to scalar ratio. And then you have phi, a lensing potential, also simulated by a Gaussian random field, expected value 0 with its own covariance operator. Okay, so this lensing potential quantifies the photon path distortion due to intervening matter. And that's through the lensing operator denoted with this bold L, so it depends on the lensing potential. And in QU map space, it's defined this way. So you take the unlensed primordial CMB field and you displace the coordinates by the gradient of the lensing potential. So that gradient then tells you, the displacement from, photon emitted location to observed location. Right, and then we have n, experimental noise, and in this talk it's a Gaussian random field, expected value 0 with a covariance operator. And then you have this A. So this A just holds a beam, a pixel mask, and a frequency cut. Okay, so that's the data. And just to get a peek at the individual components of this, let's take a look at F. So unlensed primordial CMB. Okay, so this is the E field for F and the B field. And so in this case here, I'm simulating it with R being 0.025. This is on a 455 square degree patch of the sky. And so this R quantifies the amplitude of these B fluctuations here. And you can see them better in this, this plot here. I show the band powers. So the orange here are the unlensed B band powers. The blue, unlensed E. Right, so if R is 0, then this middle plot is exactly 0. So you have this truncating all the way down. I should point out the dotted line here is so S4 type noise. Let's see, it's square root of 2 mu k arcmin on QU, and then I have a knee at 100, so you get a kick up of the noise. And so even before lensing, you only see this peak, where the signal to noise ratio is greater than 1 in this small region. Okay, so now I'm lensing the unlensed polarization field, and okay, so maybe I can toggle back and forth. So there's unlensed, and there's lensed. So it's, my resolution, as the years go by, the resolution that I produce for these images get big, and so it's sort of hard to toggle back and forth without having a pause in. Okay, well, the main point is that for the lensed E fields, the main effect is just shifting things around. So it's like a phase shift in Fourier space. For B, you get this huge additive contribution of power. So it's qualitatively different behavior for lensed E versus lensed B. And so here's the band powers for the lensed B and the band powers for the lensed E. And so you can see how much power that I've added from this lensing. And this is coming from basically E fluctuations, unlensed E fluctuations leaking into B. And then I've added noise. So this is what the data would look like if you didn't have masking or beam or foregrounds. You have the blue curve here and then the orange curve. And so the problem effectively is to take these observations and then try and infer if there was a non-zero B fluctuation at the very beginning. So it seems impossible until you realize that all of this lensed power that gets added is predominantly coming from E leaking into B with the lensing. And so just from this field alone, right, we know the E modes quite well. And you can then estimate, of course, the lensing potential from here. And so there is some hope that you can then remove a lot of this lensing contribution from B. Okay, and that removing that lensing contribution is called delensing. Okay, so right, so I'm going to focus on the Bayesian approach today, and so right, I've already said this. The goal is to infer R, and in particular determine if it's greater than 0. And so the Bayesian viewpoint effectively says the 1D curve given by the posterior in R, conditional on the observed CMB polarization, that perfectly summarizes the inference on R. And it seems almost so simple. It's not, when I saw Bayes' formula and learned about Bayes as a grad student, it's almost like, are we out of a job? It just seems you can write this down, applies Bayes' formula, and who needs a statistician? But really, to apply Bayes, to get it to work, you have to make a lot of decisions. So here's a few of them. So, what do you consider noise? What do you consider signal? And I'll be calling that prior versus posterior marginalization. How you parameterize the unknowns once you've decided what your signal is that you're going to include in your posterior. Of course, sampling algorithms, non-informative priors. And a Bayesian solution really runs into these first three right away. The non-informative prior stuff, not as much, but that's still an issue, I think. So let's start with this first question. What do you consider noise? What do you consider signal? All right, so consider the first case where we treat the unlensed CMB and the lensing potential effectively as noise, and we marginalize them out in the prior before you've actually seen the data. So how would you do that? So you want the posterior on R given the data. Just write Bayes' formula. And so really we need to figure out what this is, the likelihood of the data given R. Right, and this boils down to figuring out how to model the random field lensed CMB, where both the lensing potential and the primordial fields are random. So, conditional on R, the unlensed is Gaussian and isotropic in the EB coordinates. So now you lens it. If you condition on phi, you get a Gaussian process that's non-stationary. And then if you marginalize over phi, you get an isotropic process back, but now it's non-Gaussian. And I would really suggest that as statisticians, we don't really have a good way for writing down and approximating non-Gaussian models for random fields. So this approach really seems non-tractable. Okay, so second case, you can marginalize out F, so treat that as noise, but then put the lensing potential in as a parameter. And this effectively allows you to trade sort of non-Gaussianity in this term for non-stationarity. So you would write the posterior on R given the data as the posterior joint R lensing potential and then integrate out the lensing potential. So if you look at the likelihood in this case, okay, so now you get a Gaussian likelihood, much nicer. You get the covariance operator of the data as depending on R. Okay, so you've traded non-Gaussianity for non-stationarity, and that's sort of exhibited through this covariance. So this is CFF starts out Gaussian. When you hit it with the lensing, it starts out stationary or isotropic. When you hit it with lensing, it becomes non-stationary. And then, of course, you have these operators that have masking and beam in it, et cetera. So determinants of something like this are difficult, also even in this quadratic term. And then you have the added burden of sort of integrating out your lensing potential to get your F. And, of course, you can do that just by sampling from the joint and then discarding the phi samples. So there's some really nice work being done in this case. I would say, the first one comes from Hirata Seljuk, 2003, where they're maximizing this integrand over 5, or R being 0. And some recent work, Karen and Lewis, and then Karen, this just came out. In this last paper, effectively maximizing the integrand here and applying an Laplace approximation to do this integration.
What is the non-stationary?
So let me explain what stationary is, and it's just not that. So stationary just being that the probability distribution of the field is invariant to a fixed shift. Isotropic is invariant to shift and rotation. Invariant, the distribution, right? Yeah, so non-stationary, so this is just this lensed field here, conditional on a lensing potential is not shift invariant. So if I shifted it, the lensing signature would look different, right? And that's quantified right in here. Yeah. Okay, so the case that I've been working on is this case where you treat both the unlensed CMB and the lensing potential as parameters, run them through the posterior, and then marginalize at the end. So the thing that you want, the posterior on R given the data, then is written this way. So now we have all these three parameters. And the likelihood in the integrand here are much nicer. You have the covariance matrices CNN, CFF, C55. They're easy to work with, easy to invert. However, the problem is that it pushes all the difficulty into doing this double integral, and in particular sampling from this joint. Okay, so now let me talk about this mixed flow reparameterization and the connection to Gibbs mixing time. Okay, so Gibbs sampling is pretty ubiquitous when you're doing a Bayesian analysis. Okay, so this just shows a cartoon heuristic for understanding when a Gibbs would be slow versus fast. So left-hand side, both sides you have a two-dimensional hypothetical posterior. Left-hand side you have slow mixing Gibbs, right-hand side fast. And so the idea with Gibbs, right, is that you take a coordinate slice, so say a vertical slice, sample from one of the parameters in that slice, and then subsequently take a horizontal slice and sample along that, and then iterate. So these show a couple of Gibbs steps for this one and a couple of Gibbs steps for this one. And so, you know, generally the heuristic is that if you have high posterior correlation or a lot of posterior correlation, then you move slowly. I think the heuristic maybe is better summarized, at least it lives this way in my mind, that you know, so you're fixing one of the variables, say on the y-axis, and letting the other one vary, and looking at the log posterior, if you have this sharp variation in that slice as compared to the log variation of the full marginal, then you don't move very much in that step. Right, so for fast Gibbs, if you slice, say along a horizontal axis here, if the variation of the log posterior is on the order of the variation of the marginal, then you have something that a Gibbs sampler that moves very fast. Okay. So let's apply this heuristic to the case when we fix the unlensed CMB and the tensor to scalar ratio and let the lensing potential vary. Okay, so here's a scaled version of the log posterior. So there's a missing constant. Actually, there's a bunch of terms that I'm not including in here. These are the important ones for the moment. But log posterior, F, lensing potential, and R. So, you know, for example, one of the terms that's in these, you know, dot, 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 is this quadratic in phi. But of course, you know, this is coming from the prior on the lensing potential, which, you know, is almost necessarily going to be much wider than the posterior. So the variation here is going to have a length scale much longer than the posterior, and so we really don't have to worry about these terms. So, and indeed this term here, so this comes from the prior on F. This doesn't even vary with phi. And the problem term is this data term. Okay, so you might think that, so I'm fixing F and I'm varying phi. So the signal to noise on the E mode is very large. And so you might think that that would just cause this thing to vary sharply. So that's true. However, that really doesn't tell you that the Gibbs is going to be slow because it might just express that the marginalized posterior is tight. Right, so what tells you that this term varies too sharply as compared to the marginal is that the likely, in the posterior, the likely phi explanations of the data are associated with different E maps. Right, and so you can think of, you know, if you have a hotspot in one of your pixels that you're observing, you can explain that in a combination of ways. One, that there's no lensing there and the primordial E had a hotspot, or there's a hotspot nearby and lensing brought that into where you observe it. Right? So the possible E's necessarily have different sort of E maps. And that's what makes this thing vary too much for a fixed f, or in particular fixed e. Okay, so here's a different parameterization. And so you can reparameterize by replacing f with the lensed CMB field rather than unlensed here f. And you can go through a change of variables, density change of variables, to write the log posterior. And here are the two corresponding terms that you get when you do this transformation of variables. First thing to notice is that now the data term here, this quadratic data term, has no dependence on the lensing potential. It's all moved to this term, the prior on f. Okay, so actually this is good for CMB temperature and E. In particular, this term here varies at a much longer length scale when you're looking at temperature and just E. And that's due to the fact that lensing E and temperature is really just a phase modulation. So you don't modify the band power as much as you move through lensing space. And this term is sensitive to the band powers of the field that you're inputting. Okay, and actually, we worked with this reparameterization. Ben Golem and I, and then Marius and Ben, for temperature, and then also for polarization. However, in the case we were working with polarization, it did not. Well, what should I say? So we had to do some tricks to make it work for estimating the lensing potential through maximizing the posterior. In particular, we had to cool this spectral density for the unlensed CMB. But really, it was a blocking point for getting posterior samples. Right, and so this is where we were at maybe, I don't know, 6 months ago, or maybe it was a little bit more. But we came up with this new, what we're calling a mixed parameterization. So here's the reparameterization, F naught. So the only difference from the lens parameterization is that we have this operator D in here that we're allowing to vary with R. Okay, so you can just push this through change variables formula for densities again, and you get something like this. So now both the data term and the F prior term vary with phi. And the point of D here is to try and balance the variation in these two terms so that it more closely matches the full marginalized posterior on phi. The heuristic is essentially that D rescales the power in B so that it D applied to F already looks lensed before you've lensed it in terms of power. And this effectively makes conditioning on F naught weakly informative for phi, which allows you to make big moves in phi. Okay, so let's just take a look at this. This is the actual D that we were using in the paper, and the details will be forthcoming. But this gives you the idea of how an operator sandwiched between the lensing and applied to the unlensed can really help move in the Gibbs. So D unlensed just basically looks, D applied to unlensed E looks like E. Now we have D applied to unlensed B, which has all this power that sort of mimics what you would get, the power that you would get from lensing, but it doesn't have the mode coupling. 50. Right, okay, so now let's lens this. And you can see the differential in power from lensing is much smaller than what you would get from lensing just the unlensed B field directly. Right? So here you're going from unlensed B all the way up to lensing. And the idea is that if you're given this lensed field, you see all this power and you know that's all due from phi. Right? And so that really restricts what sort of phis, the space of phis you can move with because you have so much information. Where in this case, you're given this field, the orange, and you really can't explain all this power by the lensing potential because it's confounded with the rescaling of the unlensed B to begin with. Okay, So, all right, the full Bayes solution. So the final parameterization that we're using has this form. So we're reparameterizing f with this f naught. And also, since it was relatively easy to do so, and in this talk it illustrates d, we reparameterized phi as well to phi naught. So you have this operator d as a function of r, and this operator g as a function of a phi phi. So we're letting that vary as well. These two are diagonal operators in the spectral domain. And OK, so here is the log posterior up to a scalar constant. So here's the data term. Here is the prior on f, or f naught, and then phi, and then the priors on the parameter r and a phi phi. OK, so actually, if you look at this, so you pick up a log det of d and a log det of g when you do this transformation of variables, but it seems you should be picking up a log det of the lensing operator. And we left it out on purpose. First, it's more difficult to work with. But also, in this paper with Marius and Ben, we developed a new, an ODE characterization of pixel-to-pixel lensing, which we called lens flow. And in this characterization, you get log det of lensing equals 0. And that's provably true from the characterization. It provides some other advantages like transpose lensing, inverse transpose lensing, and things that you need to compute the gradient under this reparameterization are derived analytically via ODE dynamics. And they also give sort of facet exact delensing by simply running the ODEs in reverse, but still using the forward lensing potential, just reversing time effectively. It turns out that the ODE characterization for the posterior gradients are, in some sense, a special case of the backpropagation techniques that you get when you do gradients in neural nets. OK, so I have a bunch more slides on lens flow later, but I'm not sure I'm going to get to them. So we'll just go through this quickly. So lens flow effectively just uses an alternative expansion of the lensing effect. So here's a lensed field. And this is what you would get from a Taylor expansion of lensing and truncating. Lens flow does an ODE characterization. So it's an incremental flow on F, and done in sequence or in composition. So both give exact results on finite pixels as n goes to infinity when you use, when this gradient operator returns a true gradient. And that's where the subgrid scale fluctuations come in. For Taylens, n's corresponds to the Taylor order. For lens flow, 1 over n corresponds to an ODE time step. So for discrete pixels, when you're just mapping discrete to discrete, the determinant of this guy here goes to 1 as the time step goes to 0. And that holds for any numerical gradient that is skew symmetric. So here's a nice picture that Ben made up. This is sort of doing a rotation with a lens flow type expansion and also a truncated Taylor expansion. So 1, 2, 3, 4, 5, that corresponds to the truncation order. And so you get some sensitivity when you include higher order terms because you have these large powers in here. Where lens flow, in some sense, is smoothly sort of handles this truncation. OK, so here's what gradients with respect to the two field parameters look like in this parameterization. So here we have the original parameterization, taking the gradients with respect to those, and then pushing it through these three operators. This kind of nasty looking operator can be solved via ODE. In fact, it's the adjoint ODE of this system of differential equations. So this is what you get when you take the lens flow ODE and propagate through differentials on F and delta. Take the adjoint of this, that gives you this operator. Right, and what's nice is if you use the numerical implementation of gradient that you used in the lens flow, you put it in here, you also get gradients that respect the, the actual implementation. The numerical implementation of the gradient that you used. Okay, so here's the final form of the Gibbs sampler. You initialize your fields, A, phi, and R. Okay, so we first simulate the field F. So this is Gaussian, conditional on all the rest. So we solve it with preconditioned conjugate gradient plus simulation term. And the phi step we do with Hamiltonian Monte Carlo, so accept, reject. And for the simulations I'm going to show you, it was 35 integration steps. And then for the two parameters, A phi phi and R, right, these are just one-dimensional curves, so we can actually evaluate them on a grid directly. And the nice thing about these is that if you cache these densities that you evaluated, and then average them, you get this Rao-Blackwell estimate of the things that you want, the posterior on R given D and the posterior on A phi phi. Okay, so first simulation, this is working with sort of a CMB S4 type experimental noise in the flat sky. Okay, so here's the data, Q pixel data, U pixel data. So this is on a 368 square degree patch of the sky, 384 by 304 pixels. The pixel width and the beam width is 3 Arcmans. And the noise, again, is square root of 2 mu k Arcman. There's a Ni at L equals 90. Lmin is 30, and Lmax is 2,700, which is 75% of the Nyquist limit. And then we have this pixel mass. So all the simulations that I'm going to show you have the same aspect ratio of this pixel mask, but sometimes scaled for the sky. Okay, so here's the output of the chain. On the top, we have the R chain. So the dashed line is the truth. The truth is set at, the true R is set at 0.05 in this case. This is relatively large. And then here you have the A phi phi samples. The truth here is set to 1. The chain is started at a fiducial R of 0.1 and a fiducial A phi phi of 0.95. And right, so this is almost 5,000 iterations. So a single Gibbs pass in this code runs in about 125 seconds. So probably need to bring this down a fair amount if we're going to scale up to larger regions. But right now it runs quite effectively on my laptop. If you add the A phi phi simulations, you get up to 216 seconds. And the reason for the large addition is as you move A phi phi, you have to do more lensing and delensing to get the grid evaluations. Okay, so here are the marginal posterior density estimates. So the histogram is the raw samples after burn-in of 500. Dashed line is the truth. And you can see the Rao-Blackwell estimates in orange, tracking the histogram. And we can also get joint posterior density estimates of uncertainty for A phi phi and R. Okay, so the star is the truth. And so, I mean, it's not as pretty as these nice banana shapes, but it really suggests that the impact of having a wrong fiducial A phi phi is not going to really severely affect the R samples. And okay, so in this plot, so I'm using a G that was optimized for reparameterizing phi. Okay, 5 minutes, thanks. And just to illustrate the role in that reparameterization, I've set G to be identity. So in fact, we're not reparameterizing phi at all. And this is the picture that you get. This is run under the same exact seed, so same data. And so you can see the impact on the correlation length scale for not optimizing this reparameterization. And the other thing that's interesting is the R samples that go along with this are almost identical to the R samples in the previous case. So if you look at a feature, say there, and this double feature here, it's very similar to the case where you often have quite a wrong A phi. So this is more evidence to suggest that you can really work with a fiducial A that's wrong and still get good samples for R. So I'm not sure I have time for this, but there's some nice intuition just in the simple case where you observe phi directly with noise that suggests what form to use for this G. But let me skip this for now and give you the second simulation example. So here we're fixing a fiducial A phi. F sky is at 1.59%, so 655 square degrees. And we're going to run 3 simulations, R 0.05, 0.01, and then 0. OK, so here's the output of the chain. Right, so here we have R being 0.05, 0.01, and then down here it's R being 0. And here are the marginal posterior density estimates for R. OK, so actually this the y-axis of this plot was chopped off. This the histogram and the Rao-Blackwell density shoots up too high here. OK, so we're having, I think the main thing from this plot is to make sure that when you have 0 R, you actually get the right answer. So you go down to 0. And it's a little deceptive because, in the R equals 0 case, I actually run up against the pixelization, not the pixelization, the gridding that I evaluated the R posteriors on. And so this might, probably won't get wider, but it might, if you increase the resolution near 0, it might even get closer to 0. And I think the width here, a back of the envelope calculation, suggests that the width here is about what is predicted for the optimal R constraints. All right, and then since we have the lensing potential and the unlensed CMB maps as parameters, we can do science with them or inference with them. So here are the posterior phi sample band powers. It's hard to see, but there's the black dashed line are the true band powers. And here is a plot of the true phi map. It's weighted, in the Fourier space, it's weighted by wave number, so you can pick out more fluctuations. Here's the posterior sample average. And you can see the effect of the mask on the boundaries, the smoothing. But they track really quite well. And so you can see the band powers for this map are given in green. And they start falling off, I think this is around 400 or 500. So the band powers that you're getting out here is just truncating to the prior distribution for phi. OK, so this shows the unlensed B posterior samples. So this is the true B that we're using. And this is for the 0.01 case. Posterior averaging the B samples. This is 50% color scale. OK, and so here, E band powers, B band powers in blue. The red shows you the noise. So there's an L-min cut at 30. So there's actually no data out here or no data way up here. And so really, most of what's going on for the band powers that are simulated here below the L-min cut is just truncating to the prior distribution through R. And so when you average the samples, you get this attenuation. And there's a small sort of signal to noise greater than 1 in this small band, and that's where we're picking up the signal expressed by effectively the posterior expected value. OK, so let me show you a third simulation. This is basically just a coverage sanity check for this method. OK, so we've simulated multiple independent samples. So we have independent data sets with different phis, different unlensed CMB maps, and different noise simulations. This is on a relatively small patch of the sky, so 256 by 256 pixels, about 164 square degree patch, for R being 0.05, 0.01, and 0. And we compute these posteriors and then take the product. OK, so the posteriors for R 0.05 are given here, and then the product is the gray The same with 0.01 and 0. And basically the thing that you want to check is that the product of these are covering the truth. And so it looks like we're getting at least this sanity check is passing. There's still a fair amount to test, but we're excited about this method as being sort of a tractable way to do joint delensing and R inference. OK, looks like I'm out of time. Thanks.